In this video, we're going to talk about 6.4, which is not in our book. It's out of the Larson book, talking about surfaces of revolution. So this is not an AP topic, so you won't see this on the AP exam, but it's very closely related to our arc length, which we just talked about earlier. So our definition, if the graph of a continuous function is revolved about a line, the resulting surface is called a surface of revolution. So we've seen solids of revolution before in our work in AB calculus, where we found the volume of solids of revolution. Now we're just talking about that kind of shell, the outside part, the area. So we need to know this new term, this new word is kind of a strange one, frustum. A frustum of a right circular cone, you can see in that first figure on the right, kind of looks, I think of it as kind of looking like a space capsule type thing. It really comes from a big cone with the smaller cone chopped off, kind of like what you see there on the far right. So that middle piece there, or the bottom piece, I guess we could call it, is the frustum with the smaller cone chopped off the top. So in a frustum, the interesting dimensions are the two radii, so the smaller radius, which we're calling r sub 1, and the bigger radius, which we're calling r sub 2. And then that kind of segment, that length of that, it would be called the lateral height on the entire cone, or slant height it's sometimes called, and we'll just call it a capital L for now, is that distance, that slant distance between the ends of R1 and R2. So the area of a frustum is given by pi times the sum of the radii times L, and I'll make a separate video about where all this comes from. It's pretty quite a bit of geometry that you have to go through to figure that out, but it might be worth seeing. I'll leave that as an optional video after this one. But we'll use the area as pi times R1 plus R2 times L, that distance between the ends of those radii. Now as our delta R gets smaller, so we're looking now in the differential case here. So as we take a smaller and smaller little piece of that curve, so I guess there's a picture that goes with this, that if we have some xy axis and we've got our function and we're revolving that around, say, the x-axis, then we're going to get that surface of revolution. And we're talking about just one little tiny segment there. So we're just looking at this little piece that's being revolved around, and that's what we're talking about as our frustum. So as we have that delta R getting smaller and smaller, then those R1 and R2 that are really two distinct radii in our frustum get more and more indistinguishable. So as that delta R gets smaller and smaller, we can kind of think of that radius maybe as like that width of just that little line segment that I drew there. Or we can call R, just a single variable R, as the average of those two distinct radii, the smaller one and the bigger one. This is going to allow us to get to just a single variable. So then in our formula that we have R1 plus R2, we're going to just think of that as being R plus R. And so that leads us to our formula for that little delta surface area, which is 2 pi R times L. And for whatever reason, that the variable that's used most often with surface area is S. So we'll say S is going to be 2 pi RL, which I think becomes more memorable because in the 2 pi R, you see that as a circumference. And then that L is going to be a little bit of arc length. That's going to be that, this is going to take us back to what we were doing earlier with arc length, because that little slant height of that frustum is going to be our arc length that we did earlier. Okay, so let's see where this is going. Suppose the graph of a function with a continuous derivative on the interval from a to b is revolved about the x-axis to form a surface of revolution. So that's what we're trying to show in this picture on the left there. The yellow function, the curve y equals f of x, is being revolved around the x-axis from x equals a to x equals b. So we're going to partition that interval from a to b into subintervals. So we're looking at one of those subintervals over here in the blue. That line segment that we're going to, so this curve we're going to think of as being approximated by a straight line segment. And this is the discussion we've had before when we talked about arc length. So that little delta slant height, that delta L sub I, which is this, if we blow it up a little bit, it's this length right there. As we've seen before, can be thought of as Pythagorean, where that's going to be the square root of delta x sub I squared plus delta y sub I squared. That's going to be part of that frustum. And we're saying the r sub I is our average of the sides here. So this is like an r sub I minus 1, and that's an r sub I. But that delta r is going to get so small that we're just going to safely and reasonably replace that just with the average of those two radii, so we can get to a single variable. Now, using the intermediate value theorem, there is a point d sub I on that subinterval, so we can think of, instead of trying to, pick out these two things here, we're going to have just, we're thinking of this as maybe, that's our r right there, that average between those radii. Then we know that that's the value of the function for some value of x there. So we're going to say that radius is given by f of d sub I. Then our lateral surface area, which is now going to be, this is just a little piece right there that we're talking now, the area of this little differential frustum right here. That surface area is going to be 2 pi r sub I times L sub I. Remember, we're headed towards trying to get something that looks like a Riemann sum, so that we can go from approximating this with some discrete sums into an integral, which will give us that exact area. So our r sub I, we're going to now approximate with our f of d sub I. So that's going to be, that radius is the function evaluated at some point in that subinterval. Here's our little bit of arc length right there, but that's, as we saw in our discussion with arc length, that's not yet a Riemann sum, so we multiply top and bottom by delta x sub I. We bring the denominator delta x sub I inside the radical, and then we can invoke our mean value theorem to replace this delta y sub I over delta x sub I by an f prime of c sub I. And so then we made our way to now a Riemann sum, because we've got just these functions, values of functions and derivatives with a delta x in there. So that's an approximation, as long as we use a discrete number, a finite number of those delta x's. And then if we take the limit as delta x goes to 0, we can make that transition from a Riemann sum to an integral. So this has really so far been the understanding or justification for why we're going to get the arc length, the surface area formulas that we are going to use in trying to solve these problems. So we have a few different versions of this. Here in the green, we can see that the surface area of some curve, so we take some f of x between x equals a and x equals b and revolve it around, say, the x-axis, then we're going to get 2 pi times, this is going to be our radius, that f of x is the radius of that, and this is the little arc length piece. So the we can see here's the 2 pi r part. So the radius, if we're revolving around the x-axis, is going to be the value of the function. It'll be the f of x part. If we revolve around the y-axis, then the radius going out to our little differential slice is going to be x rather than the f of x, but our little differential arc length, or differential, yeah, I guess we'd call it arc length, or the length of that little segment. The slant height is the word we usually use when we're talking about frustums and cones, parts of cones. Then the 2 pi x is going to be that circumference part. The 1 over, with the square root of 1 plus f prime of x squared, we've seen that before. That's our little differential arc length. Okay, that's that length of that slant height, if we're thinking in terms of frustums and cones, parts of cones. Okay, well, we're getting there. So now let f of x have a continuous derivative, so we need that. We need it to be smooth. Then the area S of the surface of revolution formed by revolving f about either a horizontal or a vertical axis is going to be given by, here's the green formula, 2 pi integral from a to b of r of x, and r of x is going to be, depending if we're revolving around the x-axis, that's going to be f of x. If we're revolving around the y-axis, that's going to be just x. And then the square root of 1 plus f prime of x squared is our little differential arc length. So here we're assuming now y is a function of x. And then we talk about that r of x. Okay, now we can also, if we think of it not y as a function of x, but x as a function of y, then in the yellow you see that version. So now instead of using x limits, a to b, we're using y limits, c to d. It's still going to be 2 pi, and you're going to have a radius. So that radius will either be, if we are revolving around the y-axis, then that r of y will be our function of y, and if we're revolving around the x-axis, that'll be just the variable y. So that r of y represents that distance between our curve and the axis of revolution. Now sometimes this is written more generally and more briefly, as we see in the red, that we can replace that square root of 1 plus f prime of x squared, or square root of 1 plus g prime of y squared, by just the differential ds. So that ds is whatever arc length formula is appropriate for whether our function is a function of x or y. Then we just think of that as the ds, and it makes it a little bit more compact and I think a little more memorable. All right, let's see if we can actually do this. So the first one, we're going to use our calculator. The second one, we can, if we choose to, actually do it by hand and get the exact answer. So we have in this one the area formed by revolving y equals x cubed from x equals 0 to x equals 1 about the x-axis. So we see that in our yellow curve right here. Here's our x cubed, just that piece of it between 0 and 1. We're going to revolve it around the x-axis, and so you're going to get some, remember this is now hollowed out inside. We're just talking about the shell, the surface of revolution there, not the volume. So using our brief formula, it's going to be 2 pi, and we're going to get the integral is going to go from x limits, and we want the radius. It's going to be a function of x, our radius, and then our differential arc length. So our radius of x, since if we look at some little slice right here, a differential slice, and our radius is going to be this distance right here, and that's going to be just the value of the function. So our radius is going to be the function itself, which in our case is x cubed. The differential arc length, that ds, is going to be the square root of 1 plus f prime of x squared, since our function is in terms of x. We have y as a function of x. So we're going to need to know what is f prime of x. That's going to be 3x squared. We need that f prime of x squared, which is going to be 9x to the fourth. So our ds, our little differential arc length, is going to be 1 plus 9x to the fourth, and then the square root of that whole thing, and then that's going to have a little dx in it. So that is going to make our surface area. I keep losing my pen here. So our surface area is going to be 2 pi. Our limits are those x limits 0 to 1. Our r of x is going to be the x cubed, and we're going to get the square root of, and then 1 plus 9x to the fourth dx. We could actually do this with a u substitution and get the exact value as well. But if we just put that into our calculator, I believe we get 3.563 is going to be our surface area. Okay. Now the next one, we're going to take y equals x squared, and we're going to revolve it on the interval from 0 to square root of 2 about the y-axis. So we're still imagining taking our little slice vertically, because we're going to use a dx, a delta x here. But now our distance, our radius to that axis of revolution is going to be just the x. See how that's different than the one we did when we revolved around the x-axis? Our radius was the actual value of the function. But now, since we're revolving around the y-axis, the radius is just the x. The ds, we're still using this now. We're taking this little slice here. Still going to be a delta x there. So as we've seen before in the earlier example, we're still going to be taking 1 plus f prime of x squared, and then we're going to get a dx for that little thickness there, our delta x. So we still need to know what is f prime of x, which in this case is going to be just 2x. And our f prime of x squared is then going to be 4x squared. And so our little differential slant height is going to be the square root of 1 plus 4x squared dx. So that will make our arc length be 2 pi. We're going to integrate still from our x limits, 0 to square root of 2. And we've got our radius, which is the x, times our differential slant height, which is the square root of 1 plus 4x squared dx. So I'll go ahead and work this out using a u substitution just for the practice. We can say u is going to be that inside function, 1 plus 4x squared. That will make du be 8x dx. And so the dx will be du over 8x. So our integral, we'll leave that x there for a moment. That's going to become the square root of u. Our dx is replaced by du over 8x. That will cancel with that extra x. And I should say we still have the 2 pi. Should we go ahead and maybe change our limits to u limits? I think that's always worth practicing. So we'll call that u of 0 for now, and u of square root of 2. And we'll see what that becomes. So our over 8 here will come outside, and I think that's going to become then pi over 4. The u of 0, if we plug in 0 for x, we're going to get that u of 0 is going to be just 1. If we plug in the square root of 2, the square root of 2 squared is 2, times 4 is 8, plus 1 is 9. So that's going to make that upper limit be 9. And then I guess we're down to the integral u to the 1/2 du. So that's going to be u to the 3/2. We'll have 2/3. That's going to multiply the pi over 4. And we're going to evaluate that from 1 to 9. plugging in the 9. Let's see, we can simplify a little bit. So we can call that, I guess we're up to pi over 6. And if we plug in the 9, the square root of 9 is 3, cubed is 27, minus plug in the 1 to any power is 1, so that's just going to be 1. So we're going to get pi over 6 times 26. We can cancel that. And let's see, I think we're going to end up finally then with 13 pi over 3 is our exact answer for the surface area on that area of revolution. Very good.